Will the stress in these different shapes be the same when they all have the same amount of material in the critical section? How would you calculate stress near this hole? All that answered in today's video. Let's start with the basics. Stress in a component is force divided by the area. If the force is constant, the smallest area is the critical one, and in our plate, that area is reduced by the hole. We calculate this critical area as plate's width minus hole diameter times plate's thickness. Let's choose some specific values and calculate the stress in Excel. For these chosen values, the calculated stress is 111 megapascals. Now we can vary the hole diameter and plot how the stress changes. In the graph, I will show the ratio diameter of the hole divided by plate's width on the horizontal axis and the calculated stress on the vertical axis. I will explain why I chose this ratio in a moment. As expected, the stress increases as the hole gets larger. That's because cross-sectional area is getting smaller and smaller. Now let's solve the same problem with FEA. First, I've created geometry in a FreeCAD. Around the hole, I added a tiny zone with a depth of 1 micron on each side to be able to create finer mesh there. That 1 micron is negligible compared to 10 mm thickness of a plate, so it won't affect the results at all. After that, I have exported geometry as a step file and imported it into Prepo Max. There, I have created a mesh with a mesh refinement around the hole because that's our region of interest. After that, I have assigned the material and applied the loads on one side with the fixed support on the other. Remember, for the analytical stress calculation, we didn't need material properties because we have calculated stress directly from a force and the area. But FEA first solves the deformations of a component, and from these it calculates the stresses. So material actually matters here. I ran a solver, and when it finished, the stresses at the hole were 315 megapascals. If we add this result into our graph, we can see a large difference compared to our simple analytical solution. Let's run a few more hole sizes and compare. As you can see, all of our FEA results are significantly larger than our previously calculated stress values. So why is that? It's time to spill the beans. The stress we have calculated earlier is called the nominal stress. It's useful, but it's not the true stress at the geometric feature due to stress concentration. Stress concentration occurs when there is a sudden change in stiffness, a groove, a sharp corner, or our hole. That's where the stress spikes above the nominal values. To account for that, engineers are using stress concentration factors, usually denoted as KT. In our simple plate with the hole, this factor has been studied a long time ago. A Kirsch solution or many other experimental charts are given it as a function of geometry, especially a ratio diameter of a hole divided by the width. That's why I have used this ratio in our graph earlier. As you can see from the Excel graph, stress concentration factor decreases as the hole gets larger, relative to the plate's width. That's because larger holes changes stiffness more gradually. On the other hand, very small hole in a large plate behave more like a defect or a crack, producing sharp local spikes. If we compute the stress concentration factor for each geometry and multiply the nominal stress by it, the resulting stress aligns much better with our FEA results. Be aware that the stress concentration doesn't depend only on the geometry but also on the type of loading, or more accurately, on the local stress state. For example, a shaft with a groove will have different kT in a bending compared to a torsion, even though the geometry will be completely identical. That's why there are experimental charts for different geometries but also different types of loading. These charts are very useful for initial design estimates. Back to the original question. Will the stress differ between free shapes that have the same amount of material in the critical section? The answer is yes, and by a lot. In my runs, the highest peak stress was in a component with a radius of 3 mm. After that was the component with 6 mm radius, and the lowest peak stress was in a component with a full hole. This design was also the lightest, which is an important metric in many applications. So even though nominal stress was the same for all three components, peak local spikes were very different. So, the main takeaways from this video. Nominal stress is a useful starting point, but it doesn't capture local spikes. Stress concentration can make a local stress much higher than nominal values. Stress concentration factor doesn't depend only on geometry but also on loading, so use charts or FEA together with your analytical calculations. And that is everything for today's video. If you enjoyed it, leave a like and subscribe so you don't miss what's coming next. And if you haven't seen my video about what FEA is, definitely check it out. Thank you for watching and see you at the next one.